Hello everybody, let's just do a brief theoretical introduction to the ideal gas equation. Um, so let's start with what is a gas, I suppose. That's a good place to start. So a gas is one of the states of matter in which we have particles, which can be atoms or molecules, that move around randomly and have relatively weak interactions among one another. So as opposed to a solid, for example, where the molecules or the particles are bonded with stronger bonds and have a rigid structure. With a gas, it's a bit more loose. So they don't have a fixed shape or volume, and they occupy the space of the container in which it is held. And of course, if you open the container or the jar and allow the gas to escape, it will disperse into the air. So historically, there were some studies done with gases, some experiments, important experiments, and what they found is with certain variables, which we call state variables, are important when you want to describe the system or of the gas. So these variables are the pressure, the volume, the number of moles, and the temperature. And the ideal gas equation is PV is equal to nRT. So P is pressure and V is volume and N is the number of moles and T is the temperature. R is the universal gas constant, so that was experimentally determined. And we call this ideal gas equation an equation of state. And that is because if three of the four variables are known, then the other one would have a fixed value. Um, so just for example, if temperature, volume, and the number of moles were known for a particular sample, or gas sample, then the pressure would have a fixed value. And it's the same if you mix it around. So if the pressure and the volume and the number of moles were known, then you could then the temperature would have a fixed value. So these various state variables are related to one another, and we'll go through these relationships. So let's start with the pressure-volume relationship. So pressure is force per unit area, so it's the amount of force exerted on a region of area. We measure it in pascals. Pascal named after the Blaise Pascal. And because it's force over area, its units are Newton per square meter. And the Newton is, of course, the measure of force, but it is in base units, it would be kilograms per meters per second. And because force is mass times acceleration, so it would be kilograms and the units of acceleration, which is meters per second. So Boyle's law, one of the first observations in this gas study of the gases, Boyle found that the volume is inversely proportional to pressure. So at constant temperature, the volume of a gas is inversely proportional to the pressure applied to it. So mathematically, we'll just say V is proportional to 1 over P. Because inverse proportionality means that as the one variable increases, the other one decreases. So if you were to plot a graph of volume versus pressure, you'd get some hyperbolic-like shape, because the one is increasing and the other is decreasing. If you were to plot volume versus the inverse pressure, then you'd get a straight line. And at constant temperature, the pressure times the volume would be some constant number. And Robert Boyle, of course, was the scientist who made these discoveries. So at constant temperature, if you increase the pressure, the volume decreases. And of course, the other way around as well. If the volume is being decreased, then the pressure will increase. And then the other relationship that's important is the volume-temperature relationship. And this was Jacques Charles, and we call it Charles's law. This one says at constant pressure, a fixed amount of gas is directly proportional to its absolute temperature. So here we'll mathematically we'll say V is proportional to T. So directly proportional means that as one increases, the other also increases. So at constant pressure, an increase in temperature will result in the volume increasing. And we probably also know this intuitively, that we know that materials tend to expand as you heat them up. And we should probably mention what absolute temperature is. So it was experimentally determined that when you get to a temperature of negative 273.15 degrees Celsius, the volume of an ideal gas effectively becomes zero. So this is for all intents and purposes, this is impossible. So this sets a lower bound on the temperature. So basically what it means is that it has never been observed experimentally to have a temperature lower than negative 273.15 degrees Celsius. So we'll set that value as zero, the absolute zero. And the scale we use is the Kelvin scale, so we measure temperature in Kelvin. So negative 273.15 degrees Celsius is 0 Kelvin. So to convert to Kelvin, you just take 273.15 and you add it to the number of Celsius, and that will give you the Kelvin. So we generally measure temperature in Kelvin. So now let's look at the pressure-temperature relationship. This is Joseph Gay-Lussac, and his law says at constant volume, the pressure of a gas is directly proportional to its absolute temperature. So again, direct proportionality means both increases. So at constant volume, an increase in temperature will cause an increase in the pressure. And now we come to the volume-moles relationship. And this is Avogadro's law, which says that at constant temperature and pressure, the volume of a gas is proportional to the number of moles of the gas. And we should talk about what a mole is. The mole is the amount of a substance. So this one is quite intuitive. The more of the substance you have, the more the volume will be. And to be more precise with moles, the symbol is MOL, just mole. It's the amount, the formal definition is the amount of substance which contains as many particles as there are in 12 grams of carbon-12, which, and that this number, Avogadro's number, which is a very important constant, is 6.022 times 10 to the power 23 per mole. And this is a very big number. So what you do is to calculate the number of molecules or particles you have in a sample, you multiply the number of moles you have by Avogadro's number. So in 1 mole of gas, you'd have 6.022 times 10 to the power 23 molecules or atoms, or just particles more generally. So that's quite a big number. So let's look at a worked example. Let's read it. An air bubble has a volume of 1.10 cubic centimeters at the bottom of a 16-meter deep lake. If the temperature at the bottom is 5.5 degrees Celsius and is 17 degrees Celsius at the top, what is the air bubble's volume just as it reaches the surface? So they give us a hint here. The pressure at the bottom of the lake is equal to the sum of the atmospheric pressure, which is at the surface. So at the surface there's atmospheric pressure, but there's also pressure exerted by the weight of the water itself. And this formula is given, so it's given as a hint because it wasn't mentioned now in the slides. But the pressure that a liquid exerts is the density of the liquid times the acceleration due to gravity times the actual height. So we need to use that hint to help us solve this problem. And let's move on to solve the problem. So we'll start by drawing a diagram. So this diagram has already been drawn and labeled. So pressure at the bottom, we don't know what it is, so we'll use the hint to try and figure it out. Pressure at the top is atmospheric pressure, and atmospheric pressure is 101.325 kilopascals. That is it's normally given in the table of constants or maybe the question itself will give it. And then the temperature and height and all that we've been given. So let's try and solve this problem. So the ideal gas equation, so let's do at the bottom. So we've got pressure at the bottom times the volume at the bottom is equal to the number of moles at the bottom times the gas constant times temperature at the bottom. And we can have this exact same equation for the top. So we're going to write exactly the same thing, but now it's just top. And then the velocity, the volume at the top. And then the number of moles at the top, gas constant, and the temperature at the top. So before we even go any further, let's convert the temperature to Kelvin. So temperature at the bottom in Kelvin would be 5.5 degrees Celsius plus 273.15, and this number is 278.65 Kelvin. So we want to work in the correct units. And the temperature at the top, which is 17 degrees Celsius, also plus 273.15 Kelvin, and this is 290.15 Kelvin. And then the other thing we want to do is calculate the pressure at the bottom. So let's see, pressure at the bottom is equal to the atmospheric pressure plus rho GH. And so atmospheric pressure is 101.325 kilopascals, so that's, in scientific notation, that will be 1.01325 times 10 to the power 5 pascals. And then the density of water is approximately 1,000 kilograms per cubic meter. Again, this is a constant that is normally given. I never gave it in the question, but it's generally given. Or you'll have a formula sheet with all these constants. And the acceleration due to gravity is 9.8 meters per second. Again, it's a constant that is normally given. And then, or should be known, in fact. I think that's what normally they expect you to remember. And then the height is 16 meters. So we need to make sure the units are correct, yeah? So we've got 1.01325 times 10 to the power 5 pascals plus 1.568 times 10 to the power 5. But we need to make sure that it's pascals, so let's do the units as is. So it's kilograms times meters to the minus 3 times meters times seconds to the minus 2 times meters. Now let's see what happens here. So meters to the minus 3 times meters gives us meters to the minus 1, and then seconds to the minus 2. So this here is kilograms, meters to the minus 1, seconds to the minus 2, and this is a pascal. So at least we know our units are matching right. So if we can say therefore pressure at the bottom is if we add this up, we get 2.581 25 times 10 to the power 5 pascals. So this is the pressure at the bottom. Now from our original equation of ideal gas equation, temperature changes, the volume of course we want to calculate, the pressure changes. What does not change? The number of moles does not change. So the number of moles at the bottom is equal to the number of moles at the top. So this means if we make the number of moles subject of the formula, it will be the pressure at the bottom times the volume at the bottom over R, the gas constant, and temperature at the bottom. And this is equal to pressure at the top, volume at the top, over the gas constant and temperature at the top. So I didn't even give the value of the gas constant because it will just cancel out. And we want the volume at the top. So that's what we want. So let's make that the subject of the formula. So the volume at the top becomes, so we multiply both sides by T top, and we multiply or we divide both sides by P top. So ultimately we get pressure at the bottom times volume at the bottom times temperature at the top all over pressure at the top and temperature at the bottom. Now we've got all these values, but again we need to be careful with the units. So let's do volume at the top is equal to, so let's so what is the pressure at the bottom? So the pressure at the bottom is, we calculated that above there, so that's 2.58125 times 10 to the power 5 pascals. The volume at the bottom is 1.10 cubic centimeters. Temperature at the top is 290.15 Kelvin, and then pressure at the top is just the atmospheric pressure, so that's just 1.01325 times 10 to the power 5 pascals, and the temperature at the bottom was 278.65 Kelvin. So let's see what happens here. So the Kelvins will cancel, the pascals will cancel. So what is our final answer? If we put this in a calculator, we get 2.92 cubic centimeters. And that is the final answer. So the air bubble expanded from 1.1 cubic centimeters to 2.92 cubic centimeters. And that's one example, and that's it. All right, thank you. Bye-bye.